Welcome to this presentation on wireless networking technologies, principles, protocols and emerging trends. My name is Niranjan Weerakumara Meegammana and I will guide you through the fundamentals and advancements in wireless communication. Abstract and objectives. Wireless networking is at the heart of modern connectivity. This session will explore key areas such as network architecture, data transmission, security, and future innovations like 6G, AI-driven networking, and Wi-Fi. Importance of wireless networks. Wireless networks have transformed global communication, allowing seamless connectivity in industries like healthcare, smart cities, and autonomous systems. They enable high-speed internet, IoT applications, and real-time services. Classification of wireless networks. Wireless networks are categorized based on coverage range. Personal area networks like Bluetooth and Zigbee cover personal devices mainly used in personal and home applications. Local area networks like Wi-Fi are common in homes and offices. Metropolitan area networks support citywide connectivity. Wide area networks like Internet span vast geographical areas. Vehicle networks enable smart transportation. Vehicle networks are an emerging domain in wireless communication. They utilize wireless technology to form a mesh network. Networking models, OSI versus TCP/IP. The OSI and TCP/IP models provide a structured approach to networking. The TCP/IP layer corresponds to the application, presentation, and session layers of the OSI model. The transport layer remains the same in both models. The internet layer maps to the network layer, while the network access layer corresponds to the data link and physical layers. The OSI model divides communication into 7 layers, while TCP/IP simplifies it into 4. Understanding these models help in designing and troubleshooting network. Data encapsulation process. Data is encapsulated as it moves through the network layers. It begins at the application layer and moves downward, gaining headers at the transport, network, and data link layers to ensure proper transmission and reception. Each packet includes a header containing control information. The transport layer adds source and destination port numbers. The network layer appends source and destination IP addresses. Finally, the data link layer adds source and destination MAC addresses to the packet to facilitate data transmission. IP addressing and routing. Every device on a network has a unique IP address. They are defined by IPv4 BGP determine optimal paths for data packets. They ensure efficient data transmission across networks. These protocols enhance connectivity, reliability, and performance in modern network infrastructures. Wired versus wireless LAN. Wired LANs offer high speed, reliability, and security. It makes them ideal for stable connections. In contrast, wireless LANs provide mobility, flexibility, and easier scalability. However, wireless networks require strong security measures. They must use encryption and authentication protocols to prevent unauthorized access and ensure data integrity in network communications. Use cases for wired LANs are corporate offices, data centers, universities and research institutions, as well as manufacturing and industrial automation, gaming and multimedia production. In contrast, use cases for wireless LANs are educational institutions, healthcare facilities, retail and hospitality, smart homes and IoT, public spaces and events. An emerging area in wireless networking is autonomous vehicle networks. They require low latency peer-to-peer networking to create a mesh network, vehicle to vehicle, vehicle to infrastructure, vehicle to networks, vehicle to grid, and vehicle to pedestrians are important aspects of wireless communication. 4G versus 5G networks. 4G LTE offers high-speed mobile connectivity, but 5G enhances it with ultra-low latency, greater capacity, and AI-driven network optimization. It enables real-time applications like remote surgery, smart vehicles, and IoT advancements. With faster speeds and improved reliability, 5G revolutionizes industries, supporting seamless communication and next-generation digital experiences. 5G applications include autonomous vehicles, smart cities, IoT and industry automation, healthcare and telemedicine, augmented and virtual reality, edge computing and AI, entertainment and media, smart agriculture, public safety, disaster response, enhanced mobile broadband. The wireless applications are going to create an immersive digital environment for the society. Wi-Fi evolution. Wi-Fi technology has evolved significantly through IEEE 802.11 standards, enhancing speed, reliability, and security for modern wireless networks. The latest advancement, Wi-Fi 6, which is IEEE 802.11ax, introduces key improvements in efficiency, latency reduction, and performance optimization, particularly in high-density environments such as smart homes, enterprises, and public networks. One of the core features of Wi-Fi 6 is orthogonal frequency division multiple access (OFDMA). It allows multiple devices to share a single channel simultaneously by dividing it into smaller subcarriers. This significantly reduces latency and enhances throughput, making it ideal for applications requiring real-time communication, such as video streaming, online gaming, and IoT devices. Another major advancement is multi-user, multi-input, multiple output MU-MIMO technology. It expands from previous Wi-Fi versions by enabling communication with multiple devices concurrently instead of sequentially. Wi-Fi 6 supports 8x8 MU-MIMO for both uplink and downlink, improving overall network efficiency and reducing congestion in environment with numerous connected devices. Bluetooth and NFC. Bluetooth enables short-range wireless communication for personal devices. NFC support contactless payments and secure authentication, offering fast, proximity-based interactions for mobile transactions access control, and data exchange. Bluetooth applications include wireless audio devices, wearable technology, IoT and smart home devices, healthcare and medical devices. NFC applications include contactless payments, access control and security like keycard, smart locks, identity verification with e-passports, digital ID cards, tap-to-pay transit card. Li-Fi versus Wi-Fi. Light fidelity or Li-Fi utilizes visible light for high-speed, secure data transmission. It outperforms Wi-Fi. Wi-Fi is not blocked by walls. However, Li-Fi needs a direct line of sight, hence restricting its mobility. But more secure. Li-Fi is ideal for controlled environments like offices and hospitals. Li-Fi is a promising alternative for high-speed, low-latency, and highly secure wireless communication. Key features of Li-Fi are ultra-high speed. It can achieve exceeding 100 gigabits per second. Enhanced security. Low latency and high frequency. Low latency and high frequency allows real-time data transmission. No radio frequency interference. It's energy efficient. Transmission modes. Data transmission can be simplex, half duplex, or full duplex. They define how information will flow between devices. Simplex allows one-way communication like in radio and TV broadcasts. The data flows in a single direction without a response. Half duplex enables bidirectional communication. The data flows in only one direction at a time, like in walkie-talkies. One party must wait for the other party to finish before responding. Full duplex allows simultaneous two-way communication. It ensures uninterrupted and real-time data exchange, offering greater clarity and efficiency. Full duplex is ideal for continuous and real-time communication. Telephone calls, video conferencing, and high-speed network connections are examples. Internet protocols. Internet protocols are a set of rules that govern how data is transmitted and received over networks. These protocols enable seamless communication between devices. They ensure reliable data exchange across different systems. The Transmission Control Protocol (TCP) and Internet Protocol (IP) form the backbone of Internet communication. TCP ensures reliable, ordered data transfer, while IP handles addressing and routing. There are other core protocols, User Datagram Protocol (UDP). It provides faster but less reliable communication. Internet Control Message Protocol (ICMP). It is used for error messages and diagnostics. Address Resolution Protocol (ARP) helps mapping IP addresses to physical MAC addresses within local networks. ARP facilitates efficient packet delivery. There are other high-level protocols. They operate on the top of these fundamental protocols. Error detection and correction. Networks ensure data integrity using error detection and correction techniques like cyclic redundancy check (CRC), Hamming code, and parity check. CRC detects errors by generating a checksum based on polynomial division. Hamming code corrects single bit errors by using redundant bits. Parity check detects single bit errors by adding an extra bit to data. These techniques ensure reliable, accurate, and secure data transmission. Address Resolution Protocols (ARP). ARP maps IP addresses to MAC addresses. Reverse ARP performs the reverse. It assigns an IP address to a device. These protocols facilitate seamless communication within a local network. They ensure proper address resolution for efficient data transmission between connected devices. Analog versus digital signals. Analog signals are continuous. They are used in radio and telephony. The human voice is analog. Digital signals are discrete. They enable efficient data transfer in modern wireless communication, including mobile networks, Wi-Fi, and digital broadcast. Signal properties. Wireless signals are characterized by amplitude, frequency, and pace. They determine signal strength, speed, and transmission quality. They impact communication reliability in networks like Wi-Fi, Bluetooth, and cellular systems. High frequencies enable faster data transfer but have short ranges. Lower frequencies offer better coverage and penetration through obstacles. Modulation techniques. Modulation techniques such as amplitude modulation AM, frequency modulation FM, and phase shift keying PSK are used to encode data into wireless signals for efficient transmission across different communication systems. Orthogonal frequency division multiplexing OFDM divides high-speed data streams into multiple low-speed subcarriers and transmit them simultaneously. It reduces interference and improves bandwidth efficiency. OFDM used in modern LTE and Wi-Fi networks to enhance signal reliability and transmission efficiency in wireless communication. Collision detection and avoidance. Ethernet networks use CSMA-CD, carrier sense multiple access with collision detection, to detect and handle collisions. Wi-Fi uses CSMA-CA, carrier sense multiple access with collision avoidance, to prevent them. CSMA-CA utilizes RTS, request to send, and CTS, clear to send, messages to manage wireless transmissions efficiently. Unlike CSMA-CD, which allows collisions to occur before resolving them, CSMA-CA minimizes the chances of collisions by ensuring devices negotiate access to the channel beforehand. This makes CSMA-CA essential for wireless networks, where detecting collisions is difficult due to signal interference and varying transmission ranges. Aloha and slotted aloha. Pure aloha divides time into fixed slots and allows devices to transmit only at the beginning of each slot. It leads to higher collision rates. The slotted aloha technique reduces collisions by transmitting only at fixed time slot. It improves network efficiency and throughput. This synchronization reduces the chances of collisions, improves network efficiency and throughput. Slotted aloha is used in satellite communications, RFID, and IoT applications, where multiple devices share a common communication channel. Multiple access techniques. TDMA, time division multiple access. FDMA, frequency division multiple access. And CDMA, code division multiple access, are multiple access techniques. They enable efficient sharing of communication channels among multiple users. They optimize network capacity and performance. TDMA divides the available bandwidth into time slots. It assigns each user a specific slot to transmit data. This prevents interference between users. TDMA is commonly used in 2G GSM networks, digital cordless phones, and satellite communication systems. TDMA requires strict synchronization. FDMA allocates separate frequency band to each user by ensuring that multiple users can transmit simultaneously without interference. FDMA is used in analog cellular systems. Traditional radio broadcasting, AM and FM. and satellite communication. It is less efficient in spectrum utilization compared to TDMA and CDMA. CDMA allows multiple users to share the same frequency band by assigning each transmission a unique code. It spreads signals across wide frequency spectrum and ensures secure and interference-free communication. CDMA is widely used in 3G mobile networks, GPS, and military communications. It offers improved spectral efficiency and resistance to eavesdropping. Are hidden and exposed terminal problems. The hidden terminal problem causes collisions when devices cannot detect ongoing transmissions. It leads to data loss and retransmission. The exposed terminal problem creates unnecessary delays as devices wrongly assume interference and avoid transmission. It reduces network efficiency despite no actual digital conflict. It reduces network efficiency. To reduce these problems, wireless networks use several techniques. Request to send, clear to send, messages in CSMA, CA that coordinate transmission. Power controlling to adjust transmission power of access points and minimize interference. Directional antennas to limit signal overlap and enhance communication efficiency. Improved MAC protocols like TDMA to schedule transmissions efficiently. Beamforming and directionality. Beamforming, MIMO and smart antennas enhance wireless communication by improving signal strength and reducing interference. The traditional single input, single out CISO system uses a single antenna for both transmission and reception. MIMO, multiple input, multiple output, utilizes multiple antennas at both the transmitter and receiver to enhance data transmission. The multiple input, single output MISO employs multiple transmit antennas with a single receiver, while single input, multiple out SIMO uses a single transmitter with multiple receiving antennas. Smart antennas dynamically adjust their radiation patterns to improve signal quality. They reduce interference and enhance wireless network performance. They use signal processing algorithms to optimize transmission and reception, making them crucial for Wi-Fi, 4G, 5G networks, satellite communication and IoT applications. Wireless security standards. Wireless security has evolved from weak encryption protocol WEP to WP, then to WPA2, which introduced AES encryption for stronger protection. The modern WPA3 enhances security with much stronger encryption. It provides resistance to brute force attacks and eavesdropping. It replaces the traditional pre-shared key authentication. It also provides forward secrecy, ensuring past and future data remains secure. WPA3 Enterprise offers 192-bit encryption for high security requirements. These advancements make modern wireless networks safer, more resilient, and better protected against cyber threats and unauthorized access to wireless networks. Wireless security has evolved from weak encryption protocol Web to WPA and to WPA2, which introduced AES encryption for stronger protection. Wireless security threats. Wireless network face multiple security threats. They can compromise data privacy, authentication, and network integrity, leading to unauthorized access and data breaches. Eavesdropping allows attackers to intercept and read network traffic, exposing sensitive data. Rogue access points are unauthorized devices that mimic legitimate network access points, tricking users into connecting to insecure networks. Evil twin attacks involve setting up malicious Wi-Fi networks with names identical to trusted networks, deceiving users into sharing credentials and data. Man-in-the-middle attacks are another serious risk. The attackers secretly intercept and modify communication between two parties. Brute force attacks exploit weak passwords by systematically guessing login credentials to gain unauthorized access. Additionally, deauthentication attacks forcibly disconnect users from a network, pushing them to reconnect to a malicious access point controlled by an attack. To mitigate these threats, stronger encryption, forward secrecy, and resistance to offline brute force attacks is required. By implementing WPA3 and other security best practices, wireless networks become more resilient, secure, and resistant to cyber threats, safeguarding user data and ensuring safer communication. Future trends in wireless networks: 6G networks and terahertz waves expected around 2030 will leverage terahertz frequencies from 100 GHz to 10 terahertz. They will offer ultra-fast data rates up to 1 Tbps and extremely low latency. The use of terahertz waves will improve bandwidth availability and enhance communication speed, enabling applications like holographic communication, digital twins, and immersive extended reality. Li-Fi is an alternative to Wi-Fi, using visible light, infrared, or ultraviolet signals for data transmission instead of radio waves. It offers higher data speed. Li-Fi can reach speeds of 100 gigabits using the broad visible light spectrum. Improved security. Unlike radio waves, Li-Fi signals don't penetrate walls, reducing hacking risk and enhancing security. It is ideal for aircraft, hospitals, and underwater communication. Future Li-Fi network will work alongside an AI-driven network to create seamless, high-speed wireless environment. Key applications of AI include network automation with AI-powered algorithms. Will autonomously detect congestion, allocate bandwidth dynamically, and prevent outages. Security enhancement with AI-driven intrusion detection and anomaly detection will safeguard wireless networks from cyber threats. AI will help predict failures and automatically reroute traffic to ensure uninterrupted connectivity. Adaptive beamforming is a smart antenna technology that dynamically adjusts the direction and strength of radio signal towards specific devices, improving connectivity and efficiency. 6G will rely on edge computing to process data closer to the user, reducing latency and network congestion. Conclusion: the future of wireless networking is said to be revolutionized by key advancements in 6G, Li-Fi, AI-driven optimization, and adaptive beamforming. These technologies will work together to create an ecosystem that is ultra-fast, high-efficient, low-latency, and extremely secure. 6G networks will leverage terahertz frequencies, enabling real-time applications. Li-Fi will provide high-speed, interference-free communication using light, offering better security and reliability in environments like hospitals, aircraft, and smart cities. Artificial intelligence will play a crucial role in automating network management, predicting failures, optimizing traffic, and enhancing security against cyber threats. AI-driven adaptive beamforming will improve signal strength, reduce interference, and enable seamless connectivity for high-speed applications like autonomous vehicles and IoT. Together, these innovations will shape next-generation wireless infrastructure capable of supporting autonomous systems, immersive virtual experience, and truly connected digital world. Thank you.